Good evening, sir. Good evening.
Good evening, everyone. YouTube live started.
Yeah. Thank you. Thank you, Aldos. Jineesh, sir, shall we start?
Yeah.
Good evening. Good evening, Dr. Rajesh. Namaste, namaste. At the recording also will start the program.
This meeting is being recorded.
Once again, good evening to all of you. This is the second series on the mathematical initiative for engineers. Today's presentation is concentrating on the beauty of mathematics in everyday life. And the keynote speaker for today is Sri Jineesh George, scientist from the NPOL DRDO. A very good evening to all of you. And my duty is to welcome all of you. First of all, let me welcome our chair of this program and the panel leader, Dr. A. Unnikishan, sir, the outstanding scientist retired from NPOL DRDO. Sir, welcome into this program. And also I'd like to welcome our co-members who are initiated in this program. And also my dear faculty members and dear students joined from various parts of India. And also from our own college also, there are lots of people are joining on the way. And in simple words, let me welcome all of you. And I request Dr. A. Unnikishan, sir, who is an outstanding scientist, retired from DRDO, and my own guru for my PhD program at Kochi University of Science and Technology. He has produced more than 13 PhD scholars, and as well as he is having a PhD from Indian Institute of Science. Over to you, sir, for introducing our keynote speaker, Jineesh George.
I have great pleasure in introducing the today's speaker, Mr. Jineesh George. He is a group director of structural acoustics at NPOL Kochi. NPOL is Naval Physical and Oceanographic Laboratory, who are specializing in the design and development of underwater systems that operate underwater, using acoustic energy. So there's a process called transduction, where the piezoelectric elements produce electrical waves when excited mechanically and vice versa. So this of course is the physics of it, but to engineer this and keep it operational for a long time underwater on a moving ship or a submarine is a very great Herculean task. So this has evolved the subject of transducer engineering, and Mr. Jineesh George is heading that group right now. He's the group director over there. So in addition to this, he has also in engineering the structural these devices underwater. He has also specialized in what is called the design of acoustic domes. Acoustic domes are the ones which house the transducer, prevent them from the hydrodynamic disturbances that are appearing ahead of it when the submarine or ship moves ahead. But at the same time, it is acoustically transparent. That's the challenge. So you have a scientist today with a rich experience in the design of structural acoustics, and is a specialist in structural acoustics. They extensively make use of the mathematical skills to model their systems using classical methods like differential equations and all that. So let us hear from Mr. Jineesh George today. Over to you, Jineesh. Welcome to you. Please for the talk.
Thank you, sir, for the nice introduction. Good evening, dear students, senior colleagues, and teachers. So I'm trying to share my screen. I hope my screen is visible to everyone.
Yes, please go ahead.
Yeah. Okay, and I hope I am audible also. Okay.
You are.
Yes, please.
So I request everyone to read the quotation in this slide before we get on with the presentation. I'll pause for a moment so that everyone can do that. These are the first lines from a book called Liber Abaci. It was written by the famous mathematician Leonardo Fibonacci in the 12th or 13th century. I hope I can move ahead.
Okay.
Yeah. What distinguishes the human beings from other creatures is our ability to communicate and to count. In other words, the language and mathematics. It is an established fact that every culture became first numerate before they were literate. If you think about it, it is not very surprising. As babies, we had learned the concept of numbers before we had learned our words. When we were just 6 months old, we could differentiate between the number 1 and which are more than 1. As can be seen from this masterpiece painting by a 4-year-old child, even little children happily learn their geometry. Geometry is basically the relationship between patterns, colors, and numbers, and they learn it on their own if they are left alone. Then something happens, the formal education happens. Our schooling system, we have to admit that it's a very efficient, well-oiled machine where 4-year-old little ones are transformed into very responsible, highly responsible young citizens who are ready to take up the world. But the schools are also very efficient in systematically destroying our love for mathematics by focusing too much on testing our knowledge of things which have no value. I'll demonstrate this with a simple example. Every primary school student learns to multiply 3 or 4-digit numbers. There's a well-established procedure for doing this operation. First, you write the larger number above, then the smaller number. Then you multiply the top number, the 492 by 7, and write it down below. Then 5 into 492, shift 1 place and write down below. 3 into 492, shift 1 more place, write down below. Then you add all these numbers together and you get the answer. Bingo. You get 3 out of 3 marks in your term examination. During our primary school mathematics examinations, we are tested on how fast and accurately we can do this calculation, and almost every child eventually learns this procedure. But how many of us ever thought about the reason why we shift the places here? I did not know about the present generation, but most of the people from my generation, including me, had no clue. And we never bothered also, because we were all focused on doing maximum number of problems so that we could score maximum number of marks in our examinations. Now, the reason for shifting the places becomes very clear if we rewrite the problem in this fashion. 492 into 7, 357 is 492 into 7 plus 50 plus 300. So then we realize that these blank spaces are not actually blank spaces. These are zeros. Once we see this, immediately the light blinks. But instead of teaching this simple concept, we make the kids endure the experience of solving problem after problem, which the simplest calculator on any mobile phone can do much quicker and more accurately than us. Learning fast multiplication techniques had some value perhaps 100 years ago, but not now, not in the age of computers. The ability to do manual multi-digit multiplication quickly does not add any value to the life in this century. What we should have learned was just the concept. From this point, we move on to more complex concepts like the division, trigonometry, and algebra in the same fashion. The focus is solely on learning the formulas and applying them. Since the concepts are not taught, and these concepts are not self-evident, the students are forced to do rote learning. The advanced topics like calculus are then built on these shaky foundations. By this time, we would have started hating mathematics truly, unapologetically, and deeply from our hearts. So we carry this trauma and the resulting hatred into colleges and later into our professional lives. Making 20-year-old students like you and 40-year-old people like me fall in love with mathematics again is a process of healing the past injuries. It is like running a time machine and going back to our 4-year-old math-loving selves. So today's talk is a humble attempt to invent that time machine so that we can see the beauty of mathematics in everyday life. Let us begin. Whether in kindergarten or in engineering college, there are only 4 things that we need to learn while studying mathematics: the numbers, the operators, the concepts, and procedures. In the kindergarten, you learn to count and to represent that number as a commonly accepted symbol. Over time, we learn that the same number can be expressed in several different forms. The success lies in understanding that all these forms are essentially the same. They mean the same thing. Then there are only a small set of fundamental operators. Every other operator that we encounter are the compound operations or combinations of these fundamental operators. Then the concepts, which most of us conveniently ignore. And finally, this is where the teachers and students focus. Just a moment. I'm trying to get the laser pointer because the mouse is, yeah. So this is where the students and teachers focus because of the obvious reasons. Now, I want to make a case for shifting our focus from here to here. As I mentioned, desktop computers can do procedures better than us, but without knowing the concepts, we cannot make better computers. And it's not very difficult to learn the concepts. For example, consider this square with side A. Its area is A square. Then take another square with side B and place it in this fashion. Then you add these two rectangles, each having area AB and BA. AB is equal to BA. So now we get another square having side length A plus B. Its area is A plus B all square. And immediately, this is one of the most famous formulas in algebra. And it follows. It's as simple as that. Now you take the same square and consider this shaded area. The shaded rectangles has side A and B, and this diagonal has length C. Now I'm going to rearrange these 4 triangles. I'll move this triangle here, this triangle here, this triangle here, and this triangle will remain there. Since we have not changed the areas of this the triangles, the area of the unshaded regions remain the same. So the Pythagoras theorem immediately follows because the area of this square is C square. So A square plus B square should be equal to C square. The point that I want to make is that every mathematical theorem we learn can be broken down to simple explanations like this. Once we know this, mathematics becomes beautiful. Now let us continue with our discussions on the right angle triangles. Euclid's fourth postulate states that every right angle is congruent, which means they are equal to another right angle. It just means that right angle in this triangle and this triangle are equal. So simple and elementary, right? So why should that be a postulate? Why should that appear in a geometry book? So what's so great about this postulate? Well, it was a very important revelation when this fact was discovered thousands of years ago. In fact, this seemingly simple idea saved the Egyptian civilization from extinction and civil wars. Here goes the story. The Egyptians depended on Nile River for everything. The fields on the shores of Nile was very fertile and gave them a large quantity of surplus food. Trading the surplus grains with other cultures made the ancient Egypt very rich. These farmlands were owned by royal family and other powerful noblemen. Each had their own share of land with clear boundaries. But the Egyptians had a serious problem. Nile flooded every year with unimaginable fury. And after every flood, the entire land would be covered in silt and clay. All the boundary markers would be destroyed or taken away by the raging river. They tried placing large stones as boundary markers, but even these largest stones were rolled over by strong currents. They tried to use pillars as the boundary, but the foundations of the pillars in the flooded areas shifted because it was loose soil and there was a lot of landslide. This ambiguity in land boundaries was a serious concern, and it caused a lot of infighting among the powerful nobility. They needed a method for resurveying the land and demarcating the boundaries every year. The only thing that prevented a potentially catastrophic civil war over the land ownership was their knowledge of right angles and right angle triangles. They knew that the right angle of a triangle with sides having a ratio of 3:4:5 or 12:5:13 was identical to any other right angle. These Fropp loops were extensively used for establishing the parallelism, the perpendicularity, and distances, which formed the basis of Egyptian land surveying. Every year, they were able to resurvey the flooded land and re-establish the land boundaries. The Egyptian civilization continued to prosper for a very long time. So let us steer our direction on right angle triangles in a different direction. Let us create more right angle triangles here. We'll draw more lines. And let us assume that there are an infinite number of lines. You now see that the outer envelope of this geometry approaches a nice curve. This method of generating complex curves is known as curve stitching, and it is used in art, especially in embroidery and sculpture. And curve stitching is also used in designing aesthetically pleasing yet structurally strong suspension bridges. Little mathematical analysis will show that this curve is a parabola. From our 12th standard physics, we all know that parabola is the path of the projectile motion. A stone thrown into the air follows parabolic path. So our discussion on the right angles had taken us into the ancient history of the Egyptians. Parabolas gives us an opportunity to go into another story. This is from a more modern time, the story of Kargil War. Most of the students here were not even born when the Kargil War happened, but I'm sure that everyone knows the background. The Pakistani militants captured a few strategically important mountains in Indian territory. They did this with the help of Pakistani military during the heavy Himalayan winter season when all border posts were abandoned. Capturing the mountains was a tactical victory for the enemy because it gave them better view of the surroundings, and it also gave them a higher ground and significantly higher weapon ranges. As you can see here, our army was trying to dislodge the enemy from a lower ground, and since they were at a higher elevation, their weapons, even if they had this weapons with similar capability, their weapons were having higher ranges than ours. So it was not easy for our army to approach the intruders without suffering heavy losses. Then one option was to use the aircrafts, but it was very difficult to use aircrafts in the mountains, first of all. And in some cases, the aircraft could not fly undetected without crossing the line of control. And crossing the line of control would have escalated the situation into a full-blown war. And above all, the Pakistani military had supplied the militants with advanced anti-aircraft guns. During the initial stages of the war, we lost a few aircrafts. So the air power was mainly used for strategic support rather than for tactical mission. But being in the lower ground gave us an advantage. We were able to use heavy, higher caliber artillery guns, which could attack the enemy bunkers while staying well outside their firing range. It was not possible to carry such huge weapons to the mountains, and hence the firepower of the enemy was limited to small portable guns. The Bofors guns were ideal for this operation, since its long barrels could easily propel a bullet at velocities as high as 880 meters per second, which was sufficient to hitting the enemy while staying safely away. Before this war, the term Bofors was a highly controversial word in India because of the alleged corruption in its procurement. But if you now do a Google search on Kargil War, you will find the images of Bofors gun all over. It is no exaggeration if we state that Kargil was won by the Bofors gun. But here comes the twist in the tale. In the real world conditions, the path of the bullet is not strictly a parabola. For example, if there is a tailwind, the gun will overshoot the target. And if there is a headwind, the bullet will fall short. In both these cases, the follow trajectories are not strict parabolas. Now, let us add more complexities. The crosswind will move the bullet to right or left of the target. There is air resistance, which is proportional to the square of the bullet velocity. And this might bring non-linearities into the problem. Now, the air temperature, density, etc. vary at different heights. Hence, the air tag resistance at different points are different. So the bullets are not identical. And also the bullets are not identical. As per the gun specification, the bullet muzzle velocity varies from 850 meters per second to 880 meters per second. Finally, there can be errors in angular positioning of the guns and instrumentation errors in sighting the targets. These are all random variables and are not easy to predict. Note that we had started with a simple deterministic problem from class 12 physics. To hit the enemy, we just needed to know the velocity and the launching angle of the projectile to see if the parabola crosses the enemy bunker at this point. But now it has quickly escalated into a complex, nonlinear, probabilistic mathematical problem. This has now become a fourth semester engineering mathematics probability problem. But if you're wondering where the probability is coming from, we'll investigate. So we have a powerful Bofors gun here, and this is the enemy bunker. So if you are able to hit right over the bunker, the enemy would die. So our target is to hit this zone of destruction. But all bullets will not hit the target because of the reasons I explained earlier. But even a bullet that falls a few meters away, here and there, can cause some damage in the form of flying shrapnel. And a bullet falling nearby also has a huge psychological value. It would terrify the enemy and he will not dare to leave the cover of the bunker to target our positions. So this is a zone of influence. The shells falling outside this zone of influence does not cause any major damage to the enemy, but it prevents free movement of the militants or their supporters in these areas. So they will not be able to get any reinforcement in terms of manpower, or they will not be able to get fresh supplies, munition, food, or water. And bullets falling outside the zone of deterrence has no value. So now we'll place our bullseye here, the zone of destruction, the zone of influence, and the zone of deterrence. Let us assume that we have 10 rounds in our gun and we fire one after another, aiming at the bunker. Suppose 5 of the rounds hit the target, 3 rounds hit the zone of influence, 2 on the left and 1 on the right. So let us generate a histogram of this target hitting. So now suppose we have 100 rounds and see where all these bullets are hitting. And if we'll see that a few rounds have fallen outside all zones due to whatever reasons. But as the number of rounds increase, we'll see that the histogram slowly evolving into a symmetrical pattern. As the number of zones and number of rounds increase, the histogram will approximate a smooth bell-shaped curve. We also will see that for random processes, this curve can be mathematically expressed by a formula. This curve is known as Gaussian probability distribution. So if we understand the parameters of our gun and the environmental variables in a statistical sense, we would be able to predict the probability of hitting our target very accurately, even if we are not able to accurately predict the path of each and every bullet. The probability distributions are taught in semester 4. And you will find this bell curve everywhere. The height of students in a classroom, the vibration levels inside an aeroplane, the dimensions of a mechanical component under production, wind and wave loading on offshore structures, noise in the communication lines. Right from the social sciences to the computer sciences, the bell curve keep on appearing. Let us go back to the Bofors gun. The soldiers who can accurately make these mathematical predictions will need to fire a less number of bullets in comparison to a primitive army which relies on trial and error, who has to fire a large number of bullets for getting their targets right. Thus, a smart army with advanced mathematical tools for tactical and strategic scenario simulations and predictions are typically superior to a conventional army which relies on gut feelings and brute force approach. But how can a nation boast of superior mathematical software tools if its engineering graduates hate probability and statistics? It is not an exaggeration to state that the wars are won by mathematicians. We all know about the Eureka story of Archimedes, but he was also a war hero. He had invented several war engines and weapons based on his knowledge of mathematics and physics, which protected his tiny city of Syracuse from Roman invasion. The Second World War, coming to the Second World War, the Second World War might have been fought by the soldiers on the ground, but it was won by the mathematicians like Alan Turing, who broke the secret code of German military communications, and Oppenheimer, the theoretical physicist who led the nuclear bomb program. Again, the Bofors guns. These extremely powerful guns are also extremely noisy, and constant exposure to these high levels of sound causes temporary and in some cases permanent hearing loss among the soldiers. So one solution is to ask the soldiers to wear earplugs. Well, the earplugs will stop the gun noise, but they also stop all the useful noise. For example, the earplugs make the verbal communication between the soldiers who are operating the guns very difficult. And using the earplugs all the time can also cause the soldiers to lose situational awareness. They will not know if an enemy approaches them from the behind. But the advanced armies use smart headphones. These devices use adaptive noise cancellation algorithms, and they can cancel out high levels of noise from the guns, but they will pass low levels of sound. This selective noise cancellation is achieved with the help of wideband miniature microphones and speakers controlled by advanced algorithms. This assembly drawing shows the internal details of a typical headphone. The sound is generated by a vibrating surface. An electromechanical actuator driven by the voltage signal representing the sound causes these vibrations. In every headphone, some of the input energy will be lost as heat. So a headphone speaker or any sound transducer for that matter can therefore be approximated by the famous mass spring dashboard system. This mass generates the sound into the air through its vibrations, and these vibrations are caused by an actuator, which is expressed by the elasticity of a spring, and the energy losses in the system, energy losses in the headphone is represented by a dashboard. So we have a very simplified physical representation of our gun noise cancelling headphone transducer. There are three forces here: the inertial force, which is mass into acceleration, F is equal to ma, and damping force is proportional to velocity, F is equal to cu, and finally the spring force, F is equal to kd, where k is the spring constant and d is the displacement. So, and sum of all these forces will be equal to the external force. So now we have a slightly dangerous looking equation of motion of the headphone. But this equation will look more friendly if we remember our 12th class calculus. X is the displacement. So dx by dt is the velocity, and d square x by dt square is the acceleration. So mass into acceleration, damping into velocity, and spring constant into displacement. This is a second order linear differential equation which you will find in all fields of engineering again. For example, the same type of equations govern the LCR circuit oscillator. You will find this equation in your engineering syllabus as well. Despite its menacing looks, it is relatively easier to solve this equation in comparison to other types of differential equations. I'll not go into the mathematical solution, but I'll present the solution in the graphical form. Here on the x-axis you have frequency of excitation, and y-axis you have the vibration amplitude. So there is some frequency at which the vibration amplitude is maximum. This is called the resonance frequency. The expression for the resonance frequency is given here. It's FR is equal to 1 by 2 pi root of k by m. We'll come back to that later. Since we are speaking about the speakers, we have to think about the human audio band. Human beings can hear the sound signals in the frequency band of 20 hertz to 20,000 hertz. Please note that this is the x-axis in logarithmic scale. It's 20, this is 1000, and this 20,000. Most of the music signals are below 8 kilohertz or so. So the similar speakers work in the middle of this band, somewhere close to 2 kilohertz, up to 2 kilohertz. And these are known as mid-range speakers. But we can enjoy the music in its full glory only if we are able to listen to the low frequency band, the bass, and also the high frequency band, the treble. That is why the larger music systems have three speakers: the woofer for bass, the mid-range speaker, and tweeter for high frequencies. You might have noticed that woofer is the largest and tweeter is the smallest. That is because the woofer needs to resonate at a lower frequency. And if we look at the expression here, for having a lower frequency, the M has to be high, the K has to be small. So this expression tells us that for lowering the resonance, the mass has to be large and spring constant has to be low. So that's why the woofers are bulkier. Since the spring constant is low, they can vibrate with a larger amplitude. That is why we can visibly see woofers of large music systems moving forward and backwards. On the other hand, a tweeter needs to have a higher resonance frequency, and hence they are compact. Excuse me. Now, if we connect the audio jack to an oscilloscope, this is how a music signal will look like. This is a graph of voltage versus time. This signal contains frequencies ranging from 20 hertz to 20 kilohertz. That's why we are able to hear the music when it's fed to the speaker. But just by looking at the graph, we cannot easily make out the frequency contained in this signal. For that, we have to convert the signal into the frequency domain by applying a mathematical operation known as Fourier transform. Fourier transform of a music signal will look something like this. When such a signal is fed to the speaker, the woofer will respond to the low frequency band, the mid range will respond to these frequencies, and tweeter will respond to the high frequencies. That is because that is the way these speakers are constructed. And some people like the music with high bass effect, and some people like opera music and they like to hear the music with high treble effect. That is why the music system have bass and treble controls, bass and treble controls. When you increase the bass on your music system, what you're effectively doing is amplifying the low frequency portion of the spectrum. You raise the high frequency band if you increase the treble. A musically inclined person who has some knowledge of these basic principles and mastery of a simple signal manipulating tools like Audacity can have a good career as a sound engineer or even as a DJ. But the quality of musical experience depends on the quality of speakers you use. Cheap speakers focus mainly on the mid-frequency range because most of the sound energy is concentrated there, and they may not be able to reproduce the low frequency or high frequency sounds accurately. So in fact, the term hi-fi comes from the audio engineering. Hi-fi means high fidelity and it can represent the signal without any distortion. And a low fidelity speaker will not be able to do that. Obviously, the quality of music suffers if you use a low fidelity speaker. So now you know the difference between an 85,000 rupees headphone and a 499 rupee headphone. Both look identical, but a lot of effort goes into the design of miniature sensors and speakers of a great wireless noise cancelling headphone. These products are designed using advanced numerical methods like the finite element techniques. In the finite element technique, we divide the complex geometries into domains having regular shapes. Then the complicated governing equations are simplified to weak forms, which helps us in expressing the entire problem into a set of linear equations. This set of linear equations can be solved using matrix algebra techniques. In the first look, this process and these equations look very complex, and most of you might not have even bothered to listen to what I just said. And I don't blame you, because people tend to switch off their minds when they see these kind of menacing equations. But if you take a closer look and break down the process, you will see that the first part is nothing but the partial differential equations and vector calculus from second and third semesters. And second part is a matrix algebra that you learn in S1 and S2. These complex problems are solved using numerical methods to which you are introduced in semester 4. The finite element solution is all about inverting million by million size matrices. So now you know why you spend so much time in understanding the process of inverting smaller 2 by 2 and 3 by 3 matrices in your first year of college. And here's an interesting hypothesis. Our country's foreign policy is formulated based on the assumption that at least some of our engineering graduates will learn the principles of linear algebra and differential equations. Have you heard about no first use policy of India? India is one of the few countries in the world with a declared no first use policy when it comes to the nuclear weapons. What it means is that India will not use nuclear weapons in a war unless it is attacked with nuclear weapons. In the coming few slides, I'll explain the strong link between the no first use policy of our country and our capability to design high fidelity headphones using S1, S2, S3, and S4 mathematics. First, some geopolitics. India has two major adversaries, China in the east and Pakistan in the west. All three countries have strong armed forces and have nuclear weapons. Every one of us know that. And we have to admit, China is a larger power than us. But fortunately, China also has a no first use policy. And Pakistan is another story. Pakistan has openly declared that it will use any weapon in its arsenal, including the nuclear bomb, if attacked, if they are threatened. And this threat is of a great concern to us. So if a war happens during a war, I hope that the war never happens because it's never a pleasant experience for any of the countries which go to the war. But if it happens, and if any country is compelled to use the nuclear weapon on us, it will be an all-out assault. It will not be a single missile coming to us. It will be an all-out attack, and the enemy will try to take out maximum cities and maximum military installations in a single go. So a country with no first use policy is taking a risk. They should be able to defend this attack. They should be able to defend, and they should be able to absorb such an all-out assault and still be able to fight back and destroy the enemy once and for all. That is why we have the nuclear triad, the capability to launch the nuclear weapons from air, land, or sea. We demonstrate our weapons and our capabilities in the Republic Day parade and so that the enemy would know that we have the capability to exterminate them, so that they would not even think before about launching a missile on us. But among these three options, it is easy to detect the aircraft using radars and to monitor the land-based missile launches using satellites. Both can be easily detected and destroyed. The most powerful among the nuclear triad are the submarines. A submarine hiding at 300 or 400 meters under the sea surface is extremely difficult to detect and destroy. A nuclear-powered submarine with ballistic missile launching capability is the most lethal weapon ever invented by the mankind. A single submarine can carry enough firepower to destroy a nation. A nuclear-powered submarine can stay hidden underwater for months, waiting for the message to launch its missiles. The electromagnetic waves cannot penetrate deep into the ocean, so we cannot detect a submarine using radar or using optical means. The only way to detect a submarine is by using sound, like a bat catches its prey by listening to the echoes. It works in the same fashion. An anti-submarine warfare ship, a ship that is hunting the submarine, sends out a sound signal and gets an echo. Sometimes a ship can listen to the sound made by the submarine as it moves. Submarines also have to use sound for avoiding obstacles and for detecting the ships and other submarines. All warships and submarines are equipped with huge sound transducers for generating and receiving sound. These are called sonars, or sound navigation and ranging. This is how a ship sonar looks like, and this is a highly sophisticated submarine sonar. A widely used type of transducer, which is used in sonar systems, is shown here. It's called a Tonpils transducer. Tonpils is a German word which means singing mushroom, just sings. And Tonpils transducers can act as an underwater speaker or as an underwater microphone. And this is how these transducers are made. There is a vibrating mass, there is an actuator, and there's a piezoelectric actuator. A closer look of these two images will tell us that sonar transducer is almost identical in construction to a headphone speaker. So we can use the similar design principles and arrive at the same second order linear differential equation for a sonar transducer. It's a very highly simplified model of this transducer. Just like the bullet path in the real world is not a parabola, it is not easy to solve the real world sonar problems using single degree of freedom approximations. Therefore, here also we must use mathematical tools like the finite element methods. In other words, the engineers who understand the engineering mathematics can design better submarines, and the nation with better submarines will have better second strike capability. Such nations will be able to ascertain a clear moral superiority over its adversaries by declaring ethical policies like no first use. Now, the numerical techniques find use in all fields of engineering, right from the design of a chair to the design of an RF antenna to the crash simulation of a car. There are general purpose and special purpose software tools for modeling and analyzing these problems. To be very frank, we really don't have to understand the intricate mathematical techniques for using these tools. Anyone who knows how to use the computers can model and solve these problems. So the question is, why learn mathematics if computers can solve these problems for you? The quick answer is the output of this program depends on the input we give. The person who knows how these mathematical tools actually work can arrive at the optimum solution much quicker than someone who uses the program without that knowledge. Some advanced users even can write their own subroutines to solve the problem in their specific area of interest very quickly. So the finite element method was presented just an example, but this is true for every other engineering tool. As I mentioned, that was a quick answer. Now I'll go into the long answer. I'll try to present some compelling reasons why we should stop hating mathematics. In the nature around us, we see many interesting phenomena. We can react to these observations in different ways. One, we can believe that the world is the way it is and what happens, so happens. But this would be the lowest form of human existence. Intellectually, these people are not different from the animals. The next level is to try to find out the laws of the world. This is where most of us are. A small minority of people go a little bit beyond. They not only understand how the world works, they also try to use this knowledge for making the world a better place. This is the highest form of living, and these people occupy the apex of the human evolution. Here's an example. The spontaneous synchronized blinking of fireflies or flocking of tiny birds or synchronized swimming of a school of fish are eye-pleasing sights. But how do these creatures with tiny brains and very little intelligence manage to display such a show? Basically, these insects operate with just 3 simple rules. An insect, the rule number 1, an insect is aware of only the nearest neighbors. Rule number 2, the nearest neighbors tend to align with each other. And 3, they are not repelled by each other. Amazing, right? Only 3 simple rules behind this amazing synchronization. There were a small set of people who were curious about the synchronized behavior of insects and other creatures. They found out that this was not really a biological problem, but it was a mathematical problem. It eventually got solved and was published in the Journal of Applied Mathematics. What is the use of learning about patterns of the biological world? Apparently, this study was of immense significance. This study formed the basis for the development of the algorithms for the synchronization of electronic clocks for real-time parallel computing applications. 20 years later, we now have cloud computing, online VR gaming, and navigation with GPS. That was true innovation inspired by the nature, and it happened only because somebody translated an everyday occurrence into a mathematical problem with immense practical significance. The next compelling reason why we should learn maths is because it equips us to find rational solutions to the real life problems, like whether you should build a house or is it better to stay on rent, or if you should change your job, etc. I'm not suggesting that you should take these decisions just by comparing the financial benefits alone. It's not about number crunching. Doing the profit loss arithmetic won't help you here because the solution to this kind of problems involve emotional factors which are difficult to quantify. What I really mean is that these decisions are to be taken using a large number of factors. And the mathematics trains you to use rational thinking approach for approaching multivariable problems like this. That is because mathematics is actually a sense. Mathematics is a sense like sight or touch. To borrow the concept from Edivu, mathematics is a sense that allows us to perceive the realities which are otherwise intangible to us. We talk about the sense of humor, sense of rhythm, not about sense of mathematics. It is because we are taught mathematics in the wrong way, as I explained during the earlier slides. Most of us see it as meaningless process of mindless number crunching. But in reality, the mathematics is a sense of patterns and relationships. In kindergarten, we learn to add 2 single-digit numbers. It is a very straightforward lesson. In school, we encounter the notion of variables. Then we are introduced to the concept of functions. But what many of us fail to realize is that this expression and this expression and this expression effectively represent the same concept. When we realize this, we learn to apply the principles we learned in one situation to another more complex situation. Life is also about applying the reasoning we learned in one situation for solving the problems we encounter in a completely different situation. The more we are trained in the methods of mathematics and science, the more rational we become as a species. That is how the progress is made. So mathematics teaches us to see the logical connections in seemingly unrelated data and to find innovative solutions to the real life problems. So now I want to conclude my lecture by repeating these 2 lessons. First, mathematics is a sense. And second, mathematics means learnable knowledge. It is a learnable skill. This sense can be learned and developed by everyone so that it helps us in employing mathematical principles for calculation, application, and above all, for inspiration. Of course, I'm not promising that it's going to be a smooth journey. Mathematics can still confuse you and tell you that 1 and 0.999999 continuous are essentially the same. But that is the beauty of mathematics. Let me now switch off the time machine and bring you back to the present. Thank you.
Jineesh, it was really an amazing presentation, and really congratulate you for bringing such a really beautiful presentation by correlating the semester 1 up to semester 4 of the syllabus of engineering, particularly from Kerala Technical University, and you have made such a reference, and I'm really thankful to you. Over to Unikrishan, sir, please.
Thank you, sir.
And also we'll go for the open questions after that. Any questions from the audience? You can unmute the mic and you can ask the questions, please. I think the sharing the screen, Jineesh, sir, you can just.
Yeah, I'm stopping. I'm stopping. Yes.
Either you raise the hands. Any particular area you want further explanations or discussions, or you want to listen more about the Kargil war or anything? Unikrishan, sir, you can say some few remarks.
May I ask a very interesting question to the youngsters who are listening to this? You know why the first computer was invented? What's the name of the first computer in the world? ENIAC. ENIAC. That was invented to compute what is called the artillery firing tables. Jineesh had shown a kind of a graph that shows what angle should be chosen so that you get a proper target. This has to be pre-calculated, and during the Second World War, this was calculated and given as a table to the soldiers who are there operating in the field. So depending upon the situation hand, the turret angle has got to be adjusted. This they adjust according to looking at this table and then fire and then try to see that you get the maximum reach. Of course, all other offending forces like wind and all those things are there, as Jineesh has already warned you. But you have to definitely position the gun in such a way that it gets the maximum hit. And nowadays that doesn't happen because nobody carries these tables along with them, printed tables. There's a laptop available with every soldier who is moving along with moving ahead of this. He remains somewhere and looks at the whole angle, looks at the angle, and then pre-calculate and then communicate to the base station, where they immediately adjust the angle and then shoot. So remember, majority of the mathematical concepts have been extensively used in warfare, unfortunately. Though it is not intended for the mathematics is also used. It's required to be used for peaceful applications, but majority of them have been used in war applications. This is an unfortunate situation. So you would have also heard about the second order differential equation that he was talking about. It's a very powerful differential equation. In fact, he already cautioned you that it's also used by many others. In electrical engineering, we use it for representing resonance circuits. Only thing is, instead of M, K, etc., it becomes something else. That's all. Chemical engineers also use the same thing. Everybody, civil engineers, everybody use the same kind of equations to represent a dynamic system. Second order differential equations is a very powerful system. And the previous day, you would have heard Dr. Muralikrishnan saying that any order differential equation can be broken down into n first order differential equations. That means solution becomes simple. Instead of worrying about higher order differential equations and all the complexities involved in solving them, you can break them down into first order differential equations. And by simple manipulation, you can solve all those differential equations. So all these things you are studying as part of your linear algebra, differential equation techniques, etc., are then become directly applicable to whatever kind of modeling and design and all those things that we do in engineering. Military sites, it also happens to in other sites like engineering, construction, and all those things. So I once again congratulate Jineesh for the excellent presentation that he gave, because obviously he has covered the whole aspect and tried to relate them to which all mathematics is actually going to finally, which all mathematics is really going to be applicable for the particular concept. So congratulations, Jineesh. Let's hope that the students would pick more interest out of this and start loving mathematics and start trying to relate mathematics to realities in life. Okay, thank you.
Sir, we have a question. Is there any direct use of mathematics in industry? That is a question raised
Can you repeat the
by.
I did not get the question.
Is there any direct use of mathematics in industry?
Industry.
Industry.
Yes, but you'll see mathematics in form of computer software tools these days, because all the since computers are widely available, the mathematics is embedded inside these tools. So you'll not directly see how the tools are working. As I explained in the case of finite limit model, you'll only see a GUI where you will see 3D models, but the mathematics is inside. But if you want to modify that particular software tool to your own situation, you'll have to apply mathematics. And perhaps I cannot call that state that I am working in industry, because I work in research and development. So I use mathematics day in and day out. But in industry, this is where the mathematics is used as software tools.
And you say quality control in industry, it uses extensively statistics. Quality control essentially tells you that out of 10,000 items you manufacture, how many of them are going to be faulty. And essentially that gives an idea of the quality of the manufacturer. If out of 10,000 items that you manufacture, 5,000 are going to be faulty, there is no point in talking about that particular manufacturing process. So how to reduce the rejection rate, how to account for the rejection rate, how to predict the rejection rate, because you cannot break all of them and then try to do the testing. So there are mechanisms by which statistically well-defined techniques by which tests can be conducted and results can be extrapolated to predict what will be the kind of, how many of them are going to survive for a period of time. And the whole
actually, I want to add. I want to add one more sentence there. The management technique, which is called Six Sigma, which is a catchword, that actually comes from mathematics, comes from the probability distribution that we discussed in the presentation, and that is used in improving the quality of every industry.
And also, Jineesh, you mentioned about the automobile industry in your presentation, which you can explain further little so that it will be more clear for them.
Which one?
The automobile industries, you mentioned.
Automobile industry.
Yeah, that you can address.
Yes, in automobile industry, like right from the scratch, they use software tools for everything. The CAD tools for designing, structural design, aesthetic design, they use CAD tools, and these are all working based on principles of mathematics. The drafting tools are working based on the principles of geometry, the principles of solids and surfaces. And then the structural design, they have to design automobiles for static loads, like the weight of the passengers, the weight of the equipment, etc. And also for dynamic loads, like vibration. And also the automobiles should be designed for impact. So there are specific tools available for analyzing all this. And they do experiments for validating their analysis, but they will not be able to validate all cases. What they do is they choose specific cases and validate through experiments. But they analyze all the cases using software tools, using mathematics.
And also you can little elaborate on the civil engineering side, where you know that the structural bridges are there and the conventional bridges, which is also part of your presentation, which you can for the civil engineers benefit.
Now, possibly civil engineer can come and explain those things, like the theory of columns and all those things. Possibly a civil engineer can spend some time with the students. That'd be quite exciting for them. For though most of us would have studied certain aspect of civil engineering, it's better that the civil engineers themselves talk about it, because they'll be able to give a lot of examples.
Anyway, I can give some hint. All structures are designed for withstanding the loads of the nature. And these loads, like wind loads, and suppose you are designing an offshore structure, you have to design it for wave loads. And all these loads are like random processes. They're not deterministic. You cannot say that this is going to be the wind speed at this point of time, and this is going to be the maximum wind speed. But you have a statistics. You have some value for the average speed. You have some value for the maximum, it's called 100-year storm, 10-year storm, 100-year storm, etc. 100-year storm means that is statistically the largest storm that you are likely to encounter in 100 years. So typically the structures are designed for that. So they're also basically, it's mathematics and statistics. And even for structural engineering design also, the finite element tools are extensively used.
Okay, sir, we have one more question. Okay, how can an engineering student of artificial intelligence and data science can make use of learning the topic topology?
Can you ask the question once again? I am not able to hear that. Please speak again. Once again.
Yes. How can an engineering student? Yes. Yes. How can an engineering student of artificial intelligence? Can you hear me, sir?
Yeah. Please.
How can an engineering student of artificial intelligence and data science, okay, can make use of learning the topic topology? Can make use of learning the topic topology.
I have to admit that I am not an expert in this field. I am also I have heard about artificial intelligence, machine learning, deep learning. Our office is also trying to implement that in certain like classification of targets, etc. But I'm not an expert, so I'll not be able to comment much on that. I'm sorry.
Is Murali online? He may be able to comment. Is Murali online? Murali, are you there?
I cannot see him.
Better person to answer that.
No, Murali is not there. I think there is one more question in the chat.
Rajesh, can you answer that? Data science relating data science to mathematics.
As Jineesh said, a silence may be better at this point of time.
Data science basically relates to how to model the data streams, etc. When it comes to modeling all these things, naturally, used in the model. This leads to optimization techniques. Extensive amount of mathematics has to be studied for you to develop the proper model. Otherwise, most of the systems use some standard tools which are available. You try to model that by plugging the parameters. But the brain behind that actually would have tried to solve some of the sophisticated equations in the random process as well as in the classical differential equations and all that using optimization theory, and then try to come up with certain data models.
And especially when the systems turns highly chaotic
rainfall. For example, that's a very sophisticated model. In fact, predicting a rainfall is not a very easy joke, and even if you predict it, will not happen also, because there are so many parameters which are actually accounted. Estimating these parameters properly and plugging them properly is a very difficult task. So artificial intelligence essentially tries to find out how the data can be modeled. Observing something, how you can infer something out of it. That requires a lot of model that has got to be developed.
Of course, when the system turns chaotic and above that, modeling is again a challenge. We have to even think about the validity of the model once we develop it to some level of satisfaction. So all these requires extensive statistical and other approaches. Validity of the model itself is in question at times. And Jineesh, can you try to answer this question? Can you please throw some light on the term computational thinking, which is now coming in the chat box?
Computational? What is it?
Thinking, computational thinking. I think Jineesh might have used that word somewhere.
No, I did not use that word, and I do not understand what exactly is meant by computational thinking. Actually, I have to again remain that I'm a mechanical engineer, and for me, computation is something abstract that happens inside a computer. So but I don't really understand how the computation is.
Interesting. Can Ganguly, can you explain it further? Jayant Ganguly is asking that question.
Kindly unmute Mr. Jayant.
Yeah, sir. Can you hear me?
Yeah, because
yes,
this should start a discussion also, because we are all from different streams. Yeah. If you have some stories to share, that is always good. Please.
No, because nowadays, actually, whenever we go to some seminar, they say that mathematical modeling is more rigid. It is a set of equations which we do, but now it is an iterative process of computational thinking. So that's what in many areas like fluid dynamics or whichever area we try to apply mathematics, iterative process is getting more mileage than getting a robust model. So that is what I was thinking of asking Dr. Jineesh, that whether he can throw some light on this this aspect.
Unfortunately, I am very blind to this area, so a blind person cannot throw light. So let me, but sounds exciting. I'll go and look for that after this talk.
Definitely with the neural networks and other kind of soft computing techniques, what Professor Ganguly was trying to say is really relevant and becoming popular along with the new terms AI and ML coming into picture.
Yes.
Anyway, thank you very much for pointing it out. Some of our youngsters will further, try to understand and get involved into such activities as well. We definitely have a
Any more
session on
questions?
such topics also, because this discussion will,
No, sir.
I request the organizing team to note down this new topic, because in future courses of time, we will identify the correct persons to elaborate this, because this is going to be a continuous kind of an exercise for all of us. Very interesting exercise. Therefore, I request some of our volunteers to note down this particular topic pointed out by Mr. Ganguly, so that we will have a detailed discussion as well.
And also in the feedback form, there is a provision which you have given. What is the expected next talk? So kindly, sir, you can also mention, we will also review and pass among our apex body.
If
So
Raj
this
is
is
going
our
to take on, then fantastic. Otherwise, I'll have to talk to Shivarajan whether we can step in. Shivarajan, can we step in? Is it time for us to step in? Shivarajan, are you there?
Yes, I am today, sir.
We have already done some loose presentation to our committee. Can we make it better and present it to our youngsters?
Yes, sir.
Because I will definitely take some time, because for me preparing, I don't have ready material availability.
Okay, we can make a trial. Anyway, I request Professor Ganguly to just enter this topic there. Okay, otherwise also we have noted it down.
We'll note down, sir. We'll note down as well as in the feedback from those who are writing. In addition to this, if any other points if you wanted to make, you can also make. And kindly requesting everyone to fill the form also. Feedback form, it's a very simple one. And also in our forthcoming meetings, it will be done like this. Initially, who are coming within the 100 people will be in this Zoom, and the rest of the people will be there in the YouTube channel. So that is how we are following. So you can mention your
some of our volunteers can look into the YouTube also. If something is coming as a chat there, we can take that first.
There is already a team, sir.
Okay.
Rajesh, please, there is a team.
Try to remove that.
Recording of this webinar will be available on YouTube or not?
Yes, sir. It is already available, and immediately after this, within 2 minutes, it will be available.
Okay, thank you so much.
Yeah.
It's very informative, and we hope that in future you will deliver the next topic or more informative topics. Thank you.
Kindly fill up the form, so we'll look into that, sir. And we'll get an expert into particular areas.
Yeah, I have filled up.
I think, sir, time is also up. I think now we'll wind up, and I request Dr. M.B. Rajesh for the Art of Science and concluding remarks. Over to you, Dr. M.B. Rajesh. He's the chair of IEEE Kochi.
Thank you, Dr. Sojan Lal. Basically, what I felt today is we were not listening to an online presentation, which is very popular nowadays. Rather, it was a very wonderful, enjoyable safari to the beautiful jungles of mathematics. Mr. Jineesh could take all of us from equations to real life. And as an engineering teacher, it was an eye-opener to me that we are surviving because of mathematics. For the safety of the country as well as citizens, how mathematics plays a role. Okay, even though we are supposed to know this, but this has been particularly highlighted by Mr. Jineesh George. And as a member of the organizing team in conceiving this great idea, now I feel very proud of that very initiative that we could all take up. And see 100+ listeners for an online program like this is really wonderful. That itself shows the acceptance of our program among engineering graduates, teachers, professors, and of course our budding engineering students. And today's presentation was really wonderful. The word that we usually use is amazing. That may not be sufficient. I don't know better words. It was something speechless today. Thank you, Jineesh, for taking that great effort in making it very much suitable for the entire community sitting. It's a very heterogeneous crowd here, starting from first year student to senior scientists are sitting. But it was equally enjoyable for all of us. That is the wonderful part of that presentation, and the content and delivery was very good. We teachers want to basically imitate that. But that is a kind of input you got, and the experience sharing from people who are actually working in this area is definitely going to make a real interest in our students as well. So on behalf of the organizing team as well as all the listeners across the country, basically, it gives a pan-India feeling also. He was talking about defense, security, and we have many people from many states. It was such a feeling as well. Thank you, scientist Jineesh, George, for taking your time, sharing it with all of us. Thank you very much. I would like to very specially thank Dr. A. Unnikrishnan, who is leading this mission and guiding all of us and planning all the strategic operations related to this community. Thank you, Dr. Unnikrishnan, for your very wonderful leadership roles that you are making and in this transfer of knowledge to the next generation. Thank you. I would like to congratulate and thank Dr. Sojan Lal, who is a very active professor and now the principal of MBITS, who actually has conceived this idea of making a love to mathematics, and it is now proved to be very successful. Thank you, Dr. Sojan Lal. We will continue this mission. I think it is going to be endless because today also we got some topics newly. Every day we will get topics like this, and we will be able to continue that. I thank him from my heart on behalf of all who are now beneficiaries of this program. Great idea that he taken forward. Thank you, Dr. Sojan. And any program, especially online, is challenging if we don't have active participation. And I am happy to see that even now, vote of thanks usually people will skip, but even now we have 100+ in Zoom and YouTube. Thank you all the listeners. Actively participate. I request every listeners here to communicate that this is happening, and please share our notices and invitation to all your colleagues so that it becomes more and more meaningful, and the students and enthusiasts from any part of the country can join. And even if you have some suggestions on the timing and other kind of logistics as well, please get back to us through the feedback form. With these words, I would like to conclude and would like to thank each and everyone assembled here for this very fruitful discussion today. Thank you very much.
Anyway, we'll be sharing this YouTube link to all the participants who even registered. More than 400 registration again. See, I'll share with all of you. And I'm sure for the coming generations, this will be an inspiring day, and they will be definitely watch this. Jineesh, once again, thank you for bringing this one. Dr. Unnikrishnan, sir, this is because of your able leadership, we are able to do this, and thank you again, MB Rajesh, for coming. And thanks for all of you, and thank you. We are closing down. Thank you. Bye. Please fill up the feedback form, please.
Thank you everyone for the opportunity. Thanks a lot.
Thank you, sir. Thank you, dear. Looking forward.
So I hope I can leave now.
Yeah. We are closing down. Thank you.
So should I end the meeting?
Feedback link still. You can stop the recording. Feedback link is reposted if you want. Maybe you can also share with the people who who are not able to come back, so that we will share this YouTube as well as the certificate. YouTube lab can be closed.